All right. So, hello everyone, and it is my distinguished pleasure to invite our next speaker in our flagship research colloquium series in the ECE department. Our next speaker is Dinesh Bharadia from University of California, San Diego. He has been a faculty in ECE since January 2018, and he received his PhD from Stanford and postdoc from MIT. His research interests include advancing the theory and design of modern wireless communication and sensing systems with applications to robotics, health, and everyday life. Much of his research has inspired new research areas for broader communities, from communication theory and circuits to RFIC and robotics. He has also applied much of his research work and translated it into startups and commercial products through companies such as Hyla, Kumu Networks, Totemic Labs. Specifically, he has built a prototype of a radio that invalidated a long-held assumption in wireless, that radios cannot transmit and receive simultaneously on the same frequency, leading up to a new research direction in full duplex radios. He has commercialized his full duplex radios, which went into deployment with Deutsche Telekom as well as SK Telecom. The product is currently under development, and he serves as a technical advisor on multiple startups. In recognition of his work, Dinesh has been named to Forbes 30 Under 30 and also a Marconi Young Scholar for outstanding wireless research. He was also awarded the Michael Dukakis Leadership Award and was named one of the TR35 by MIT in 2016. Without further ado, I'll pass over the mic to Dinesh to take us on a journey on wireless sensing and robotics. Thank you.
Thank you, Akshay, for a warm introduction and probably a little bit longer than I anticipated, but I guess I need to update my bio. All right. With that, so I think my group and I have been sort of working on this wireless sensing, and we started doing a lot of robotics, and I've been just going to take a little bit through this journey, right? And probably skip some of the motivation so I can cover more ground and tell you interesting ideas. And since a lecture, I will keep it as a lecture form. So let's see. So wireless sensing, right? The way I think about wireless sensing is very simply following, right? Whatever you can do with camera, right? Imagine you can do the same with the wireless, but even behind wall and other cases, right? So just to give an example here, right? Okay, this is a work and slide image from Ming Ming. He's behind wall on this, and you can still create his pose while he's behind wall, right? So simplest example, right? So think everything you can sort of imagine to a large extent with you can do with camera, you could do with wireless sensors, right? And in last decade or so, a lot of my community and their other work I've been posing here, right? And with their appropriate, and you had one of them as speaker in this colloquium as well, right? So now that this has been done, right? The problem is this works well in bad weather, it works in non-line of sight, and there is an extensive infrastructure, right? I like this GIF very nice because it's sort of like, hey, it's like a Superman with his eyes, but it just uses Wi-Fi device, right? I think it's a very cute one. That's how you should sort of think, right? So the problem has been that this wireless sensing hasn't sort of translated into mainstream applications, right? And mainstream deployment, right? And so when I started, right, I was just thinking about what is the key problems, right? And a lot of this was inspired by me sort of talking to, we're trying to commercialize, as you guys heard, right? Been into commercialization space, right? Our work on wireless localization back in 2013, right? And we realized like the problems we could solve, right, were not good enough for it to be actually used at a large scale, right? One, the biggest problem was that we can't provide context with wireless sensing, right? So just to think about simply, right, okay? Camera, you can see an image and you can say what's going on, right, roughly, right? But that's not true with wireless, right? The information you have is like a wireless channel, right? How the reflections behave and so on and so forth, right? And you're just trying to infer based on that everything, right? So partly this lack of context, right? And also knowing the environment, right, through this wireless sensing is extremely challenging, right? So that was on one side. The other thing which I was noticing back when I started this in 2017, right? Robotics has been doing pretty amazing, right? They have built robots which can go into environments which are challenging, right? They can be extremely small sized. And they are soft robots which can do a lot of interesting in-body and out-of-body stuff, right? And even robot dancing, right? I think this shows that, right? So now, the issue which basically you can think of this following, right? I think the review of the last decade, or at least from my point of view, is that we sort of built robots to be autonomous, to do the same task humans do repetitively, but more autonomously, right? So, but the challenges which are faced by robotics often are how do they sort of operate in challenging environments, right? How do sensing rise to a point where they can work in these environments, right? Okay. And interestingly, if you think about it, right, wireless sensing can do a lot of these challenging sensing for them, right? There is like lack of this interconnect between these two fields in some sense, right? And by no means I'm saying that I'm going to do the entire thing, right? But I'm just trying to invite everyone to sort of join in this theme, right? So let me make one more slide and make this point more clearer, right? So I think in most wireless sensing, you're doing these experiments in this lab setting, right? Which is still reasonably big lab, but still it's really a big deal to translate it to these large environments from the lab, right? So that's the challenge faced by wireless sensing, right? How do you take the research which works in lab and sort of generalize it to larger environments, right? And the vice versa is how robots are very pervasive in the sense that they are used for so many things today, from self-driving cars to Teslas to robots which are delivering food to you in your hotel rooms, right? All of this is taking place, right? They are maneuvering and going to larger and larger spaces, right? Okay. But they are challenged with the sensing, right? One is a popular example of weather, right? Being problem for self-driving cars, right? Working alongside with humans, right? That's another challenge with these robots face, right? So now, what I'm sort of bridging, and this is where I sort of came to this, right? These two fields can solve each other's challenges, right? And that's where it sort of this title came along with, right? So in my lab, we have sort of built robots which sort of goes around, maps physical environments, and also maps the wireless infrastructure out there, right? Okay. So this was one side where basically we are using robotics to power our wireless sensing and to make a large scale deployment, right? Then we did a data-driven, because we collected a lot of data with this robot, we could do data-driven localization and many other sensing tasks of wireless, right? And then we sort of generalized this to user devices like our phones, right, to IoTs, like even low power tags, all type of infrastructure you can imagine, right? I think we have different work on different scale on these things, right? All the way up to 3D localization in very small form factor, and even building RFICs. So the point is, we sort of have focused on one, robotics driving wireless sensing on one side. And the other side we have been now recently focused on is using, sorry, this slide has, in any case, we'll just stick with this. The other way around, that how can we use wireless infrastructure as a robust mode of sensing, because it works in non-line of sight, inclement weather, right? So we have showed how you can build SLAM algorithms on top of wireless, right? Even how SLAM can be combined with heterogeneous camera-based sensing together with wireless sensing, right? And then how wireless can be used to do even perception systems, and now even developing new sensing which sort of gives human-like sensing capabilities to these robots, right? Okay, so all right, I'm going to now speed up a little bit, right, and sort of start with the first topic in some sense, context, which is basically one of the key problems wireless sensing faces is that they don't have context, as we discussed, right? So how can I provide this context, right? And I'm going to start with simple information like physical map, right? So let's take an example application of wireless sensing. A most typical wireless sensing application is localizing my phone, right? I can't have, it's just here, but assume I could localize that phone and which is on me, right? The problem is that the entire last decade of research sort of assumes these knowledge of these access points in your environment, and then in abstract space gives me a location 19,13, right? Which has no meaning, right? Ideally, I would like this, for example, a blind person here, it shows like a robot, right? To give this information of where there is a furniture, where some objects are out there, right? And help them avoid collision, for example, right? Now, if I had to do this, right, with a smartphone, right, I lack this context. I can only just tell right now 19,13, right? To more concretely, right, there are a lot of tools on mapping out there, right? You go to airport, you see your dot on the map, right? It's actually very inaccurate, right? More to the point, it cannot capture detailed abstractions like furniture and new moving things in your environment at a rapid pace, right? So to this end, we actually build a robot, right? This robot is basically a platform which is most popular platform out there, right? But we combine together with a Wi-Fi client and sort of have open source this robot, right? I think everybody can try in your labs, just use it, right? I think, and there is a lot of ROS nodes deployed for this, right? You can just install, do a Docker installation and sort of get this robot up and running and you can get data from it, right? And it's autonomous, right? So this is what it does. It can just sort of go into environments, map their physical locations, what they are going on, right? And beyond that, it also maps the location of the Wi-Fi anchor points, right? So where are these Wi-Fi anchor points, right? Okay. So now, this is great, right? I'm not going to talk about the details of how you build the robot. I think you're welcome to explore it. It's all online, open source, right? You can try it out. Now, this robot finally tells me where this access point is in this physical map. Now, if you do 19,13, right, you can have a physical location with context of where you are in this environment. Okay, so that's the concrete message, right? So now let's see what is the new thing you had to do to localize these anchor points in this physical map, right? I'm gonna not bore you with this, but the reason when you go to airport and your locations are inaccurate is because airport and everywhere else you sort of use this RSSI based localization. It's sort of understood to be very inaccurate, right? And just basically uses received signal strength, right? There is a more popular form of localization, which is called channel state information, which is basically uses wireless channel to do localization. And let me give you a tutorial of how one of these channel state information based works, right? And we want this to be actually used in airports and other places. Only then we can do these collision avoidance and some of these use cases we are imagining. So let's take a look. So here's how it works, right? You have a phone, you go to airport, multiple access point sort of looks at your signal, right? And they could triangulate you, right? Basically calculate the angle of your phone from each of these anchor points and then sort of localize you, right? Now this is great in principle, right? The problem is the angle of arrival, right? Or the triangulation, right? The way it works is that you measure this additional phase traveled, right? To calculate this angle of arrival, right? Now, this additional phase traveled is then decompensated with the distance between these two antennas to figure out your angle of arrival theta, right? Okay, so this is good. Now, if I had to build actually the system which I'm anticipating the robots do the Wi-Fi mapping, I need these things to give me accurate information about these Wi-Fi access points or these Wi-Fi radios, right? And that includes this distance d, right? Interestingly, and I'm not gonna, so there are three types of error you could have, right? One is that this Wi-Fi infrastructure, you have a translation error in it, right? That will cause the location to be shifted, right? You can have rotational error, which is the worst you could have, right? Because it sort of has significant location changes if you have a rotational error, right? So, and I can go into more other details, right? And there are other types of errors, right? But the key is this orientation error, right? And interestingly enough, this is an extremely sensitive error. Like if you have a millimeter amount of error, right? Millimeter error between the distance estimation, you get large amount of localization errors. So this is where we had the first work, right? And what it does is that it has this autonomous robot which does millimeter accurate mapping of your existing infrastructure, right? And this sort of transcends the state of art on all of the Wi-Fi localization. And now you can think of a lot more applications of this in the world of metaverse and many other applications you could think of, right? Okay. So let's take a look at how it works, right? So one simple idea would be, look, these robots are equipped with a lot of sensors, which allows them to map the physical environment and know where they are located in this physical map, okay? So you could take many such location of this robot to try to triangulate exactly where this access point is, okay, right? And this works fine, right? The problem is it cannot achieve millimeter level accuracy, right? Two reasons for this. One, the robot's location itself has a lot of error or 10 centimeter or so error, right? Okay. And the second thing is that, and we tried this experiment, we averaged over many locations and we figured out that we can best case get to 3 centimeter accuracy for the access anchor point locations, right? This is not good enough, right? Furthermore, the second thing which impacts in getting these location of these anchor points or the distance between these two antennas is really you need millimeter accuracy, right? Okay. And multipath sort of impedes with this, right? And you might have seen some other similar references in localization. But let me tell you a different way to sort of achieve this, right? So the idea really is that the reason this separation of multipath and accuracies are limited is your bandwidth of the Wi-Fi communication is limited to this 160 megahertz, right? So we actually realized, right, instead of using bandwidth, right, can we use carrier frequency? And these carrier frequency for most wireless things are on the order of gigahertz, right? Which means that, let's take an example wave, right? You have one full wave and it covers sort of 6 centimeter, right? And it gives you 360-degree phase shift, right? And most of these radios are like accurate to the order of 6 degrees. So you can easily get to a millimeter level accuracy with this information, right? Now the question is, how do I use this information, right? We'll use the same or reverse of the concept we sort of learned, right? And then this might get a little bit more mathematical and detailed, right? But beyond that, I promise I would be very quick on explaining some of these ideas. So this is the only interesting idea I thought was very fun, like, and suddenly the lights were like, we just thought about it, right? So, but basically the point is following, right? I have two parameters to estimate. One is the distance between the antennas, and two is the orientation of these anchor point in reference to the robot or the environment, physical environment, right? To solve for those two parameters, and if I had only phase as a measurement quantity, right, okay, between these two antennas, right, I have two variables to solve for with one sort of phase measurement, right? And worse yet, this phase information goes into mod calculus, meaning you can get same phase and you can have 2 pi wrapped around and you will get the same information again, right? So each time you measure something, it's not an invertible function directly, right? So this is sort of what the equation comes out to be, right? And the crisp point is that basically we have sort of 2 equations and 3 unknowns, right? Okay. So I'm going to give you an interesting idea, right? The idea is that you look at the phase difference, and from that you can sort of, if you know D, then you can sort of interpolate on the other side, right? And this only works when D is less than lambda by 2, right? So what happens, let's say if D is greater than lambda by 2. So here is an example, right? If you have D over lambda to be 1, right? The same function, right? You can measure this quantity on this side, right? And therefore you can't predict this value unless you know D exactly, right? So now what we designed, and this was really creative, and I think this could be used in a lot of other applications where you want to do millimeter accurate localization and tracking. So we looked at something called rate of phase change, right? Okay. So this is what I'm plotting now, rate of phase change, right? The same 2 examples I have on the left, right? If I sort of use rate of phase change, I could essentially sort of predict exactly how we can sort of kind of estimate D and angle of arrival theta, right? Now, the whole point is that this then we deployed into a large space, right? And we used the same calculus and we showed that we can sort of get to the requirement at the 80% probability, and it sort of works 150x time better than the state of art, right? In terms of what it can give. So this was a major shift and jump in terms of the accuracy of what you could get out of this. So now let's take a look at I'm going to skip some results here, right? Okay, and this is the output sort of you see with our a real-time demo for robot. As it goes around, it discovers new access points. This is the access point and its orientation here in this physical map, right? Okay, so, and at this point in time, we are sort of working with Cisco to try to work with them and deploy this in real world, right? Let's see how it goes, right? So the next thing is that in this previous experiment, right, when we had this robot running around collecting a lot of physical map and the Wi-Fi location, we sort of also got a lot of data, right? A lot of channel information at each point, right? Could we have used that to improve localization? Meaning, if I take my smartphone back into this environment, right, can I get more accurately triangulated, right, using this data, right? So the issue with the current localization, right, is following, that our median errors are in few decimeters, which is great, but once it starts to go to the 90th percentile, your localization accuracy of your phones and these things starts to become extremely bad. So in this case, now we sort of build to the next thing, where we sort of applying deep learning powered. And the next important concept I want to take home from this talk today is this, right? Is to take this wireless channel data and represent them as images, right? And this is where I'm going to sort of show this next technique. So basically, we sort of have this extensive data, right? With this deep learning based system, right? We had this bot collected both visual and Wi-Fi data, and we use that together to sort of form a deep learning driven localization system, right? And the idea is it solves for, there are two problems in localization, right? One, you sort of have this multipath, which essentially confuses your direct path, right? And therefore makes you think that is the phone here or is the phone located somewhere in this direction, right? So that's one problem, multipath. The second problem is you don't even have a direct path. And then in this case, you definitely think that your phone is somewhere here instead of actually here, okay? So now these two problems are sort of challenging to solve because you need a little bit knowledge of the environment, right? When the path is blocked, when it's not blocked, right? And so we decided, can we go data-driven way to sort of solve this problem, right? Now, here's the problem, right? The problem is that your wireless channel or the channel in general is just a whole bunch of complex numbers at different subcarriers and so on and so forth, right? Now, and a lot of people just took this complex channel information and tried to apply a lot of machine learning models to it, right? And turns out they don't learn well, right? Because CNNs and even complex CNNs are not well designed for sort of these problems, right? And you're not representing the information in a format which is easy to understand for a deep learning to predict it well. So the question we were asking, right? We have a lot of this data, right? Can I take the wireless channel data and also represent this as an image, right? So the idea is following, right? Remember I told you about this angle of arrival measurement earlier on, right? So what if I could take this channel information, right, and project it into this complex number into a sort of angle of arrival on y-axis and time of flight on x-axis, right? Sort of creating a heat map of sorts, right? This you can take, it's a very standard transform. You can take this information from the Wi-Fi channel, right, and translate into this axis, right? Now I have translated into this, right, and it captures some real information about where the location, like the angle is whatever the angle is here, right, and sort of the location maybe 10 meters away or so, right? So though this transform is good, but it doesn't incorporate the physical information about the space into this, right? So the next thing we do is that we take this image and then translate into Cartesian by taking this access point location into account, right? And so this is here where your access point is, and this is sort of at 30 degree, right? And at this distance away. So now this is a new representation which we have come up with, right? And this is an extremely powerful representation and can be used for not just localization, but also to combine with the physical map and then do a lot of deep learning together with the physical map and the actual triangulated location which the network thinks, right? And I'm going to give you, and the output can also be represented as the location where actually the device is, right? So with this, basically it became an image translation problem, right? And let me just give you the network and how it sort of works, right? So you have images about your phone from multiple access point in the environment, right? And you sort of are trying to predict where the actual location is at. And it tries to solve for multipath, non-existence of direct path. It also solves for some time of flight errors, right? Sometimes you have a lot of errors because you don't even have absolute clock between the transmitter and receiver synchronized, right? So all this, it works very well, right? Okay, and the only insight is following, right? Even from multiple access point, right? The only thing you know is that the device is located at one single location, right? And this is what this network is trying to learn, right? And on top of this, you can overlay the physical map and give exact user location. And furthermore, right now we're looking into how you can use the physical maps attributes to combine together with this information and sort of learn a lot of machine learning and deep learning to use that information to your advantage. Now, I'll tell you about the setup, but we created 2 different setups and we see a lot of improvement of 85%, and it even achieves super resolution, right? But let me go to the one important interesting part, right? And it generalizes across environment. Even when we moved around furniture in our environment, the network worked even in those cases, right? So it's very interesting. So the thing which is very interesting is for you to look into is this. So we have a competition right now going on, right? Which is essentially to take this data and build your own deep learning network, AI network, and sort of predict locations, right? And we have, the deadline is mid-December. So if you want, you can start even today, right? It gives you at least 1.5 months, right? Okay, and these slides will be available if you want to take photo, go for it. All right, so what I have told you, I've told you how, for an example of Wi-Fi localization, I can help you with sort of building the physical map, deploying at a large scale. This robot autonomously goes, figures out all these access points, collects a lot of data, and on that data you can apply learning to essentially predict user location, right? Okay, so now that's basically this slide sort of summarizes, right? Okay, you can imagine when you go with your phone next time into the same environment, right? It can give you this exact detailed attributes, right? And we have an app which actually does this, right? And this now we have also translated for BLE. We did a Bluetooth based localization, right? Okay, there are some interesting problems there. Then we also sort of translated this to how it can be used for UWB, your air tags, right? How can they be accurately triangulated with physical maps information, right? Okay, and then again, you can look at a lot more of these, right? So we actually use this for even during pandemic for COVID tracking, right? And we are trying to create space and time social distancing using this, right? And basically it used all of this effort and paired it up, and we deployed at UCSD campus to sort of do this COVID tracking, right? In any case, this is what basically was covered in media and so on and so forth, right? So what are next steps and future in this, right? So the idea really is, how can I sort of do, not even want or have a robot go around, right? Can I sort of create a digital twin, right? Sort of the environment, and then mimic these channels, right? Learn from those and then directly deploy in real world, right? Without even requiring this robot to sort of go around and do these environment level traces, right? And that's what we are sort of focusing on, right? And again, this is like a lot of our efforts are, we have a lot of this physical space data. Can we sort of create the same in the virtual space and establish this mapping? And how do we go about establishing this mapping, right? So, all right, we are at halfway through, right? Okay. And what are the other sides of this, right? I think the other side of this is very creepy in the sense that, you know, you have my phone right now, right? My phone continuously transmits wireless packets, Wi-Fi, Bluetooth, right? And any adversary can use some of these ideas and triangulate every single person's location, right? Worse yet, right, they don't even need to host a Wi-Fi access point. You're just interacting with your UW Wi-Fi access point. Somebody put few more access points of their own, triangulated you, and can triangulate your location, right? And they can do it very precisely. And more interestingly, right, when you're connected to UW network or an authorized network, right, you don't do MAC address obfuscation, right? So you can't even obfuscate to these things, right? So the question is, how do I design my communication systems now so that they obfuscate my location, right? This is like, and we have been working on something very interesting on this, right? How we sort of are preventing unauthorized localization of user devices, right? And helping us in some sense in this, right? One should have a choice on, hey, I want 1 meter localization accuracy to be shared with Google's or Apple's, right? I want it to be 10 meter, I want it to be 100 meter, whatever your preference is, right? I think really you want to encode that information out there. Now, sorry, this slide is still broken, but let's transition to the next phase. And here I'm going to go a little bit more fast to show you what all is possible today, right? And you can use this in your efforts or research, right? Sort of went into two technical detailed concepts. One, how you get millimeter level accuracy in localization, and how you sort of represent your data into images, and which you can leverage then to do physical and digital sort of connect this intertwine, right? Okay. Now, the first thing which I think a lot of the robots today use SLAM, and this is key for autonomy, right? This, you see two robots from two popular companies, right? And the key idea is they keep going into an environment, right? And keep traversing it until a point when they see the same object again, and that's how they construct the entire map, right? Sort of like a large correlator, right? Okay. Now, imagine doing this, and the problem with this is following. You use visual sensors for this, right? Camera and LiDARs, right? And what's challenge with this? The challenge with this is that you sort of put a pot here, and this looks like exactly same as that pot on that side, right? So all these aisles in all our environments are structured, right? And what the structure does is that every sort of location in this environment looks visually very similar. And therefore, when they are trying to correlate back to finish the loop closures, right, these SLAM algorithms starts to not do well or are not robust to these monotonous environments. Now, in contrast, right, okay, I showed you how to get these images in the last discussion, right, and localization, right? So let's take a look at what happens if you have a Wi-Fi sensor and if it goes on these same monotonous environment locations. These are the same images I showed you how to get previously, and you can clearly see they are very distinct. Even though at these locations, the robot, if it looks forward facing, it gets exactly monotonous view, okay? So the idea is now to take these information, right, and build sort of a SLAM on top of Wi-Fi, right? And this is where this paper sort of is already available online, again, all data sets, right? So the idea was to use two-way bearing information, right? Okay, your robot has a Wi-Fi access point. We can get this bearing information, and this bearing information is what we sort of represent in these images, right? Even with multipath, it will create a unique feature for this sort of location. Each location has its own uniqueness. Now, this is essentially what we sort of use, right? And we designed this a GT-SAM based framework, right? It's all open source, fully available. It sort of takes the bearing information of both the access point and the robot and uses this to sort of build a SLAM on top of it, right? And it outperforms, actually, we could replace LiDAR right now. That is where we are right now stand, right? So we did this experiment in large monotonous environments like these, right? And also simple office environments and so on and so forth. And what we found is it's like more than 1 kilometer of sort of SLAM algorithms, right? And I'm going to just quickly say following, right? RTAB map is the most popular form of environment, right? Okay, which uses LiDAR and cameras. And then P2 SLAM uses just camera and Wi-Fi. So you can essentially replace Wi-Fi with, replace LiDAR with Wi-Fi. Okay, that's what basically we are trying to demonstrate here. And we get similar performances. It also shows how it sort of corrects for drift with only camera-based networks, which is what camera faces a lot of problem with, right? So basically it builds a robust sort of loop closure or SLAM algorithms just using Wi-Fi. Now, we sort of looked into how we can sort of take this and help visual SLAM algorithms as well, right? So one of the biggest problem with the visual SLAM algorithms is that they try to keep doing loop closures, right? And this loop closures, what you need to do is you need to store in memory all the previous locations you have been to and keep correlating with the new location you see. Is it the same original location amongst all of them, right? So this is a very computationally heavy process to conduct, right? Worse yet, you have false loop closures with this, right? And it's essentially one of the key problems these robots face. So in this context, right, we decided, since you have so many Wi-Fi access points around you, right, and they are all stationary, can you use them as a reference marks, right, and to perform these loop closures, right? Again, we use the same idea, or not same, but we develop a new framework, right, to perform loop closures, right, where we sort of use these L1, L2, L3, which are like landmarks in the environment, right? And these landmarks are nothing else than your actual access points, okay? So the point is that if you had landmarks, you could have avoided loop closures, right? And we basically show in this work, Vivid, right, that we can actually, hopefully this video will play, right? And you see this robot is sort of moving and it's discovering new APs, and as it discovers new APs, it does loop closures more quickly, right? In comparison to the traditional behavior on the left, which sort of still is doing these, look at this trajectory on this side, right? It's doing paths where actually there is not on the physical map possibility, right? So clearly this is like extremely fast, right? Not only that it's extremely fast, right? It's sort of also, I'll show you, Chimera is a state-of-art network, which is what robotics people use, right, extensively. And Vivid sort of beats the performance of that in both translation and orientation error of the mapping. Beyond that, you have 4 times improved memory consumption because you don't need to store all these past observation extensively. Furthermore, you can also have improvement in the compute you need to use, right? 2x less compute you need to, or you need to use 50% of the compute you would have used otherwise, okay? Again, this is also open source. Go ahead, try things out and see how it works for you. One final, or I think I'm at 11:08. I think I still have maybe, I guess, 5 more minutes in retrospect. So all of us know autonomous driving, right? And there are different levels, right? So just to give you a sense, right? Everybody wants to sort of go to at least level 4 at this point in time. Most cars are out there are in level 3, right? So some sort of human supervision is required, right? And the ones which are sort of level 4 are only in nice environments level 4, right? Where there is no inclement weather, right? Like no snow, no fog, right? So I'm just showing you some of the cars and where they stand, right? Nobody is at level 5, right? Okay. So the challenge in achieving level 5 autonomy is this, right? Okay. So as you increase fog, right, you can clearly see from top to bottom, right, your view and the ability to see the environment has become almost negligible, right? So LiDAR and cameras, because of the wavelength, they cannot penetrate through this inclement weather, right? And they're completely blocked, right? And in this case, actually, what we showed is pointillism. It's a work where basically it sort of uses millimeter wave radars to work against this adverse weather, right? And The problem with the millimeter wave radar is, or benefit is following, right? It works at a millimeter wave frequencies, which is millimeter wavelength, right? And it's far larger than whatever the inclement weather particles are, right? Snow, rain, all of these are much larger generally from a millimeter wavelength, right? Therefore, the radars can penetrate through them very nicely. Now, on this, we sort of build a 3D bounding box, and this was in 2018, sort of detection and first large open source data, which sort of influenced many people to start working with radars, right? So let me just show you some example radar and LiDAR. So this is the LiDAR point cloud of this car, and you can see clearly a lot of density, right? On the other hand, radar has only few points, right? So the whole point and the problem is following, right? When a light signal is incident, it gets reflection in each direction, and therefore you get denser point clouds. In contrast, when wireless signals are incident, they are reflected in specular fashion. What it means is that no signal is going back to the radar, or very few of them make back to the radar, and that's why you see very, very small amount of point cloud. Now, this is called as specularity, or a problem of specularity, right? Now, we developed a lot of interesting multiple radar placement and together combining their data to get more denser point clouds, and we also figured out how you place these radars, what is the right way to place them, how to have overlap, right? And again, the idea really is that we develop this technology, it collects very good high density point clouds even with radars, right? It's like LiDAR like radar, okay? Now, and then on top of that, we ran a deep learning network, right? And it gives you good 3D bounding boxes, right? And prediction from radars, and it even works in bad weather. I'll show you a demo. Or actually, let me skip this and just show you the demo. Hopefully this will work. Any case, it probably doesn't seem to be working at this point. The videos doesn't. Any case, I'll figure out and post this later on. In the interest of time, I have 3 more minutes, and I'm gonna probably just tell you about an interesting force sensor we developed. So force is something unique. Whenever we interact with our environment, it's force we use, right? To lift this phone, to lift this chair, or anything we interact with, force is the key thing, right? And the reverse of this is haptic sensing, right? Which is what the AR, VR, and the metaverse is trying to get to, right? So, and interestingly, these force sensors are very much intensively used in the surgical instruments as well, right? So just to give you an example, this is an example use case where you want to avoid this organ, right? With this probe you are bringing into the body, right? And as soon as it applies contact, if the force is beyond a certain point, you want to stop there the procedure, right? So you want your entire length of the robot to be sensitive to the force. Our hand by default is sensitive to the force, right? It's not like pressure sensor. Pressure is an average quantity. Force is like if I apply a little bit force here, I can sense it, right? Can we have our robots also have sort of this sort of sensing capability, right? And actually, we developed this force sensor, and people do this right now. So they put a lot of these sensors along the periphery of the robot, and each of them you have to have a wire, and all these wires are prohibitive, and they take a lot of power and everything, right? It makes it extremely hard to deploy. Imagine this, right? It's like very impossible to deploy, really. Well, it's not impossible, but it's reasonably hard to deploy this. So in this context, we actually came up with an interesting idea. So the idea is following. We have a 2-layered robot. Wherever you apply a force, right, it sort of deforms. Whenever it deforms, it sort of changes the reflection of this antenna. And we sort of sense these reflections to figure out the amount of force applied, okay, right? And I'm gonna just leave you at this slide where we'll show you the latest sensor. This is our 2x2 millimeter latest sensor, and it sort of has an RFIC integrated, and you can apply on any robot today, right? So we put this robot, we deployed a few sensors along the length of this robot, and it was used in different application, even in body, and we sort of showed that this works really well. Hopefully this video, any case, it shows that whenever you sort of apply a lot of force, it detects that force, and it's accurate to the ground truth sensor, okay? And we sort of use this robot to take inside body and do some experiments with this. And hopefully we are soon launching some clinical trials around this idea and getting into that. In any case, I'm going to stop at that and take question with leaving at this slide.
Does anybody have any questions?
I have a question about this soft robotics application at the very end. So when you're doing a sort of reflection sensing for easy ray signal techniques using Wi-Fi, you don't have necessarily context of your environment inside. And so are there similar issues where you have to worry about obstacles, inside the body?
So actually, force is the way to get context inside the body. Actually, that is the way right now everyone is progressing in this space, right? Like you can put cameras and other sensors, but it's really hard to even see what the camera is seeing and make what it really looks at. So like we think about environments, like physical environments, and we see the lanes and the roads, right? Think of force as also a way of doing that, right? Like you apply small force and you see if it's pressing too hard, right? Then you sort of sense, okay, I don't think I should be going there, right? I should pull back. So inside body, I can imagine the entire SLAM algorithms which you have to build inside body will be very much on a force as a key sensing paradigm, right? And obviously you can integrate together with camera, but force gives you, like, if you're pressing too hard, too small, right? And interestingly enough, right, what happens is that your robot may have gotten to a different point ahead, right? But at some previous point, you're exerting too much force for some unknown reason because some body chemistry changed at that point in time. And it's almost really hard to detect if you're actually seeing force at the tip or at this midpoint, right? And this is where the sensor is so neat in this regard that it can give you fine-grained force information along the length of the entire robot. Okay, that's a good question, and this is a good idea and research to sort of look into, right? How even with simple piezo-based force sensors, right, you can look into this in-body SLAM, and yeah, it's a very interesting area and hot topic at research at this point in time.
Any other questions? Maybe I'll ask a question while you guys think. In the deep learning part, where I think what you were doing is localizing your cell phone with respect to some images.
Yes.
Can you also use that to build a map of the reflectors or the objects that are creating all of these different images?
Yes,
Okay.
I think, or at least we are working toward that. And this is where basically, if we could construct that digital twin idea, right, where we are sort of simulating wireless channel and the physical environment, right? Okay. Based on that, we can sort of start doing much more fast iteration and understanding of, can we detect reflectors, can we detect environments. Like, as I said, right, I think of Wi-Fi or wireless in general as sort of a camera which is better than optical, right? Okay. So you should be able to do what you're just saying, right? Like map this entire environment. This is the large size, right? And even better, right? Because I can go behind walls and whatnot, right? I should be able to map what's in that environment and what's in this environment and sort of do that, right? So definitely a possibility and an interesting research problem. Not a lot of good solution at this point in time, right? So it's a definitely good tool you can use. And if you're interested, you can look at the data set, because the data set we have, right, it has synchronized LiDAR, camera, Wi-Fi, all of these data is available, right? So you can try yourself your new ideas and see if I can do this or not, right, or that or not, right? So one key focus I've been keeping, all of the projects I've showed you, right, all of their data sets, everything is publicly available for you to try it out, right? If you want to commercialize that, I'm more than happy to help you with that as well, okay? Yeah, thank you, that's a good question. Very interesting topic to do.
So, question about the localization. Seems like so it has to work with several router, and I was assuming it's probably using Wi-Fi 6 technology. I was wondering if that also worked for lower version of the Wi-Fi.
So I didn't follow. Can you repeat your question a little bit towards the end?
So for the localization, like when you do the demo, I saw like so many router, like they kind of have to collaborate so that we can have the map, right? And I was immediately think about Wi-Fi 6, which is something like Google Nest. Does that also work for the lower version of the Wi-Fi protocol?
Yes, it does. Yes, it does work with that. So way to think about Wi-Fi and actually Wi-Fi 6, there is right now a standards body standardizing how we can get channel state information available for future standards and more to the point for every standards, right? So today many chipsets already support CSI information, right? So you can definitely get the CSI information very easily. Now, interestingly enough, you don't need your Wi-Fi access points to provide you with CSI, right? You don't need to collaborate. The robot itself can collect both sided CSI because when you measure channel, right? You measure channel from this side, but you measure an entire 4x4 channel. So no collaboration from environment is also required, right? So you just need to change or just install our Wi-Fi access point on your robot and you're good to go. And you can do a lot of these mapping and all these interesting ideas. Does that answer your question? Hopefully it does.
Great. Well, thank you again for coming. Let's thank our speaker again, and we'll see you next week.